is joint work with Salil Vadan. A quick reminder of what differential privacy is in a big picture. So we have this thought experiment that if we pass in two databases differing in one person's contribution, X and X prime, we pass it through our algorithm. We're going to require this as a randomized algorithm, which we call a mechanism. And out comes an output, but because of the randomness, we actually get a distribution of outputs, whether we start with X or X prime. And differential privacy is usually stated that we require these distributions to be similar in some sense. But from another perspective, we could think that given the output, it should be difficult to infer which input we started from. So the key ideas with differential privacy is, one, we need to introduce noise, and that this results in some constraint on the algorithm. So the two questions that we're going to focus on in this talk and in this paper, in this project, are one, how can we add the least noise necessary? Or another way of phrasing that is, how do we fully use the privacy budget? I will make this precise in a moment. And then a seemingly unrelated problem is the construction and properties of private hypothesis tests subject to the constraint of differential privacy. And it turns out that these two seemingly unrelated questions are actually very closely related through this new concept we proposed called a canonical noise distribution, or CND. Now we define it with a certain list of properties we would like. There's no reason to think such a thing necessarily exists. So we give a construction that we can always produce a CND. And then from the CND, we move to the hypothesis testing problem. And it turns out that this notion of CND is exactly what we need to derive free private p-values. We'll explain what we mean by that precisely. Uniformly most powerful tests for Bernoulli data. And we might, if we have time, touch on an application to another testing problem of two proportions. So differential privacy, we could formalize it as follows. We have a privacy mechanism as a set of distributions indexed by possible input data sets. And then now this notion of closeness is governed by these parameters epsilon and delta, where we want the probability of any possible sets of outputs is similar, whether we start with X or X prime. So this was one of the earliest notions of differential privacy. It's still very common, and it's one way of formalizing that big picture. So that's our constraint, our privacy notion. How do we achieve it? Well, there's lots of mechanisms in the literature, but the simplest conceptually is to simply add noise to a statistic. The noise needs to be scaled according to what is called the sensitivity, which measures how much the statistic T changes if we were to change one person. So the sensitivity is kind of capturing how much one person is contributing. We scale the noise proportional sensitivity so we can cover up one person's contribution. There are lots of choices for the distribution we could use. Two of the most common and the oldest ones are the Laplace mechanism. This is this double exponential shape, and this can give us epsilon 0 dp, called pure differential privacy. And another very common choice is the Gaussian mechanism, which gives epsilon delta. Okay, so we've got an idea of some types of mechanisms. Let's go back to our notion of differential privacy. So we mentioned the big picture that we could also think of this as making it difficult to infer which database we started with. And it turns out that this can be formalized in terms of a hypothesis test, that given the privatized outputs, trying to discern if we started with X or X prime, it turns out that type 2 error is bounded below by some function of the type 1 error. This has been noted in several previous works. This lower bound is a little complicated, but if we plot it, we see this is a piecewise linear bound. So this plot, we have the type 1 error on the x-axis, type 2 on the y-axis. The point 0, 0 would mean no privacy. We can perfectly tell whether we start with X or X prime. And the line y, 1 minus X, is perfect privacy, where we can't tell anything. So we have this blue region is the set of valid type 1, type 2s that would give us privacy. But once we look in this perspective, we might ask, well, why should we use a piecewise linear lower bound? Why not a different one? So this is formalized in what's called F differential privacy. This concept is proposed by Dong, Roth, and Su in an excellent paper called Gaussian Differential Privacy. And so they think about what are all the possible lower bounds that make sense. Well, intuitively, it should be one of these so-called trade-off functions, which is a plot of type 1 versus type 2 error, also known as an ROC curve. And so F differential privacy says that the mechanism, when we apply it to X or X prime, the trade-off function should be lower bounded by F. And we can choose F depending on what sort of privacy definition we want. So in this plot, we have the black curve is the F, which is our lower bound, and then a few options of trade-off curves. And the only one that would satisfy F differential privacy is the red one, because it's the only one fully above. So this is the framework we're going to be working with in this talk. A few properties to motivate why we want to use this formulation of differential privacy. The first, coming from a statistics background, it's nice to have a statistical understanding of privacy in terms of hypothesis tests. That makes it a little easier to communicate what we mean by this privacy constraint. It is a complete generalization of epsilon delta. So we already saw that epsilon delta is one instance of FDP. So we're not losing anything by using it. And FDP is in one-to-one correspondence with a family of epsilon delta guarantees. And this is shown in this plot here. If you take a tangent line of F, you can convert that to an epsilon delta guarantee. And if you were given all of the epsilon delta tangent lines, you could form the original F by this contour. In the Gaussian differential privacy paper, they advocate for Gaussian DP, which is one instance of FDP. And they also prove lots of properties of FDP, that it's closed and tight under lots of different privacy primitives, such as group privacy, post-processing, composition, and subsampling. And in fact, you can prove that it's tighter than the divergence-based notions of DP that are also popular. So just a little bit of an advertisement for FDP and why we're going to work with this notion. So we talked about Laplace and Gaussian noise. So we could look at those trade-off functions and see how they compare to the epsilon delta lower bound that they achieve. Well, so on the left, we have the Laplace trade-off, and we see that it does not match the epsilon 0 lower bound. There's this blue region where they differ. And the same story with Gaussian noise. It doesn't match the epsilon delta. So in some sense, they're not fully utilizing this privacy budget because they're not matching this lower bound. And that's kind of what motivated the first part of this project, which is how can we match the lower bound? And if we do that, what are the benefits? So it turns out the concept to formalize that is the canonical noise distribution. So the conditions are a little technical, but in this box here, the basic idea is that adding CND noise needs to, one, satisfy FDP. That's the minimum. But also we want it to perfectly use the privacy budget. And that's something that Laplace and Gaussian do not do. So these two properties that we want are summarized in 1 and 2, or formalized in 1 and 2. So one says if we add delta scaled CND noise to statistic S, we should get FDP. 2 says the trade-off function of the shifted CND should equal F. 3 gives a closed form for the trade-off function of the shifted CNDs. This can be interpreted as saying that when I'm testing between the CND and the CND shifted by 1, the optimal rejection region should be a half interval from X to infinity, basically meaning that higher values give more evidence of the one shifted to the right. And finally, that we want this to be a symmetric random variable, which is not too much to ask. So this is a wish list of properties we would like to have. It turns out there are a couple instances of distributions that satisfy these properties. One is the truncated uniform Laplace or two-lap distribution proposed by myself and my old advisor, Alexandra Slavkovich. This is related to the staircase mechanism and discrete Laplace mechanisms. And it turns out that this is a CND for epsilon delta dp. And almost by definition, normal noise is a CND for Gaussian dp. Okay, but what about other Fs? So far we have no reason to think that there exists a CND. So we're going to go ahead and try to construct one. So we're given a trade-off function F. Oh, sorry, before we go to construct, we can observe an interesting relation, a recurrence relation that a CND has to satisfy. And this follows by property 3, it's not hard to show, that if we know the CND value at one point, then adding any integer, we can derive its value by this recurrence involving the trade-off function. So given this recurrence, we might have the idea that if we could somehow specify the C and D values on an interval of length 1, the recurrence would then fully specify the C and D, and we would have our construction. And that's the idea. But it turns out you can't just choose anything on this interval. You have to be a little careful. So here's our result showing the construction. We take a piecewise, a linear function on -1/2 to 1/2, chosen in a careful way, so that when we apply the recurrence, this results in a continuous distribution. And so the recurrence here is the same as the one we saw before. And we prove that this always gives a canonical noise distribution, starting with any trade-off function f. To get a picture of maybe what these things look like, here we're applying it to the trade-off function of shifted Gaussians. So on the left, we have the CDF of the CND. It is, in fact, linear on -1/2 to 1/2, maybe a little hard to tell. And then applying the trade-off function for the recurrence, it becomes nonlinear. And on the right, we have the density plot. And we see that the CND from our construction is not the same as the normal PDF in both our CNDs. So this shows that, at least in this case, the CND is not unique. So transitioning to the private hypothesis testing. So here we're going to define a test to be a mapping from the input data set to 0, 1, representing the probability of rejecting. And to implement the mechanism, we'll sample from Bernoulli with this probability. So the first lemma shows that using the quantile function of a CND, this again follows by property 3 pretty easily. If you apply F inverse to phi, you get something that has sensitivity 1 for any FDP test. Doesn't matter what you start with, how you built it, it will have this property. And so we could add noise to it from a CND, and we would get a statistic T that satisfies FDP. So we started with a binary accept reject test, and now we have a test statistic. And it turns out by property 2 that post-processing this gets us back the exact test we started with. So we got something for nothing, really. We have a test statistic with the same power. We could also get a p-value that's perfectly valid. This might not be super powerful, but in part 4, it says that if we have a null hypothesis that's a singleton, this p-value is actually equally powerful at every alternative. So something about this CND is allowing to get us a whole lot of results for free. No cost of privacy, they're all a post-processing. Okay, but you might ask, well, okay, how should I even construct phi to begin with? Well, in this one example where we have Bernoulli data, a binomial test statistic, we can give a very clear answer that there is a uniformly most powerful FDP test. In fact, the test can be written as the CDF of the CND. Again, the non-uniqueness doesn't matter here. It's any CND you pick will have this property. And we can also get a p-value that's equally powerful at all these alternatives. So this is kind of the best possible case, although it's a very simple example. And this is extending some results, prior results with my advisor, Alexander Slavkovich. Now, maybe I'll just give a really brief overview of an application where we're looking at another testing problem with two populations. So here, there is no UMP FDP test. We can show this through a counterexample. So what we do is we weaken the privacy guarantee to prove a lower bound, or let's say upper bound on the power. We propose a new test statistic and show through simulations comparing it to this upper bound that it's almost as powerful as we could possibly be and has very accurate type 1 errors. So the CND formalizes the concept of fully using the privacy budget. We give a construction that we can always build one, and it gives a lot of nice results in hypothesis testing as well as this new application. So this is available in archive. If you're interested, please take a look and feel free to contact me. Happy to answer any questions at this time. Thank you.
Thanks, Jordan. So do we have any questions? So far, I can't see any on Zoom or on Slack. But maybe, so one question I have is that there might be multiple mechanisms that do use okay, oh, actually we have a question, sorry. So Aurélien, do you want to unmute yourself and ask it?
Sure. Hi. Thanks a lot for the nice talk and the nice paper. Okay, so this went also a little bit fast for me who are not so familiar with FDP. So maybe this is a naive question, but I was wondering a bit if you could discuss or summarize a bit the concrete benefits that we can get from using a CND distribution. So for instance, can you show kind of better utility for the same privacy, maybe in the worst case, or maybe not in the worst case, but in some cases? Can you elaborate a bit on that?
Yeah, sure. So I'd say the clearest results are these hypothesis testing results where we're able to get optimal tests or these p-values that you can't do with other distributions. It has to be a CND. In terms of like other notions of utility, like maybe the variance of the noise, a CND doesn't necessarily optimize the variance. So for example, the TULAP, which is a CND for epsilon delta, for some values of epsilon, could have a higher variance than Laplace noise. So sometimes maybe you don't want to fully use the privacy budget if you have a particular type of utility in mind. In the case of if the data is exactly shifted by one, we do have a result showing that it's strictly less noise than any other distribution. But if you have something that's shifted up by less than one, it might not have that property anymore. So that's where the Laplace could actually end up doing better.
All right, thanks a lot. That clarifies things.
Okay, I think Daniel has another question.
Hey, Jordan.
Hi, Daniel.
Hi, great talk. Yeah, I learned a lot just listening. So I was wondering, I think you mentioned earlier during the talk that like you might get different results when applying FDP versus divergence-based notions. So I was wondering like what results do you get in that case? And like for, let's say you fix the type 1 error, for example, and you're trying to maximize the power. So can you say more about the differences in, let's say, power maximization for the first case? I mean, FDP versus any kind of divergence notion?
Well, so if you're using different notions of privacy, it's a little harder to compare. But I think the key thing is that F differential privacy gives a more accurate tracking of like the privacy loss than a divergence based. So for example, if I convert from FDP to epsilon delta, and I convert from a divergence based DP to epsilon delta, I will get a better epsilon delta using FDP. And another way of thinking about it is I can convert losslessly from like, if I know the F, I can get the divergence. If I know the divergence, I can't get back F. So I lose information by going to the divergence. And in some cases, maybe it's not a lot of information, but there is some information lost.
I see, thanks.
Maybe one more example is the Gaussian DP is incredibly similar to zero concentrated DP. It turns out Gaussian DP implies zero concentrated, but not the other way. But Gaussian noise satisfies both of them. So this is another case where it's like you lose just a tiny, maybe a little bit of information by going to the concentrated DP.